Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to my class. Today I will hold lecture number 13. Now this is you know that this is module number 3, and in this module we have already covered concept of wavefront and then Huygens principle and its applications. Today we will talk about superposition of waves. Now superposition means we are taking into account more than one waves. And what will happen if we have more than one waves and they are overlapping in space and time. Now we know that the dynamics of a wave is governed by wave equation, okay, and this is the expression for a wave equation in 1D, and psi is the wave function, x is the direction of propagation, t is the time, and v is the velocity of the wave in the medium. Now suppose there are n number of waves which are overlapping in time and space both. Now say psi 1 is the wave function for one of such waves, and this psi 1 would be the solution of this wave equation 1, okay. And if there are n number of such solution, then their linear combination will also be a solution of this second order partial differential wave equation. The properties of this wave equation is that it is second order, it is partial, it is homogeneous equation, okay. Now the linear combination of all these solutions which are psi is here represented by wave function psi, which is function of space and time, as you can see here, and this linear combination is represented by equation number 2. Now since psi i's are the solutions of wave equation 1, therefore the linear combination will also constitute a solution of this equation wave equation 1, and therefore equation number 2, that is psi, will also satisfy equation number 1. Now this property suggests that the resultant disturbance at any point in a medium is algebraic sum of the separate constituent waves. Okay. It means that suppose we have two waves which are propagating in the same medium and they are overlapping in time and space. Therefore, the resultant wave will be algebraic sum of the two waves, and this is what being said here in these lines, okay. And this is exactly the principle of superposition is, okay. If we have n number of waves which are propagating in a particular medium, and if they are overlapping in space and time both, then the resultant wave will be algebraic sum of all these n number of waves. Now we will exercise this superposition principle and see what would be the resultant, how would the resultant look like, okay. Now to address this problem mathematically, several equivalent ways have been proposed to address this problem mathematically, because this problem is nothing but addition of waves. Yeah, we are adding two or more overlapping waves, that is all what we require to do to come up with the resultant wave function. And what are the properties of this overlapping wave? They have same frequency or the wavelength, they are propagating in some medium, and they are overlapping in time and space, okay. Now there are different approaches using which we can address this issue, address this problem. The first one is algebraic method, where we represent wave our wave function psi as a sin omega t minus kz r cos omega t minus kz. Second method is complex method, where we represent our wave function in complex form, that is psi tilde, and then psi tilde would be equal to psi naught e to the power I omega t minus kz. This is the second formulation or second representation of the wave. And third is the phasor representation. Okay, in this phasor representation or phase addition, we just represents the wave in a vector form and add them vectorially, and the resultant will give you the final addition. Now, out of these three methods, we will learn or we will talk about only algebraic method. They are equivalent method, therefore, we will pick one of the three. Okay. Now, in algebraic method, we will start with the solution of the wave equation, which is represented by equation number 1, which was there in our previous slide. Now, a solution of the differential wave equation can be written in the following form. Okay, and this form is given by equation number 3, which is E, which is function of x and t, is equal to E naught. E naught is nothing but amplitude, and then sin omega t minus in bracket k x plus epsilon. Okay, where k is our wave vector, we know omega is angular frequency, epsilon is initial phase. Okay, any initial phase. This is the general solution of the wave equation 1. Now, you see that in the phase part, there are space dependent component and time dependent component. Okay. Now, let us separate the space and time part in phase. The space part can be written as alpha, yeah, and alpha would depend upon x and epsilon, and therefore, the expression for alpha would be minus k x plus epsilon. Now, if we do this, then the final solution or final expression of the solution of the wave equation will look like this, and this is represented by equation number 5. Okay. Alpha is the phase part which depends upon the space, and it also includes the initial phase, and omega t is the time dependent part. Okay. This is one of the solution of the wave equation, and any wave can be, any harmonic wave can be represented like this, yeah, by equation number 5. Now, we will, once we know the expression of a harmonic wave, we will consider several such waves and then let them overlap or let them superimpose, and then we will calculate or we will try to find the resultant. Yeah, how to find the resultant? The superposition principle says we will have to add them up, okay, and the addition will give the resultant expression. Okay. Now, suppose there are two such waves, first one is represented by E1 and second one is represented by E2. E1 is given by E naught 1 sin omega t plus alpha 1, and E2 is given by E naught 2 sin omega t plus alpha 2, where E naught 1 and E naught 2 are nothing but amplitudes of these waves. Okay, and the phase parts are given here. Yeah. What would be the resultant? The resultant would be the linear superposition, okay, because the linear superposition of psi i's gave us the resultant psi. Yeah. Therefore, we just added them up, we added E1 and E2, which gave us the resultant disturbance. Yeah. Now, let us substitute the expression for E1 and E2 from equation number 6 and 7, and after the substitution we get expression number 9. Okay, this is the expression of the resultant disturbance. Yeah. Now, let us expand the sine function and see what does it gives. Now, if you expand sine, then you will get these two expanded expression of sine. By using formula sin a plus b, we will get these two expression for the sine function. Okay. Let us rearrange them. Let us take sin omega t common and cos omega t common out of the given expression. Then this is time independent component, and this is also time independent component, and time dependent components are cos sin omega t and cos omega t. Okay. Now, since this term, the first term in the bracket on RHS of equation number 11 is independent of time. Let us represent this time independent part by E naught cos alpha. Okay. Similarly, the multiplication factor of cos omega t is replaced by E naught sin alpha. Yeah. This is the term which is sitting with the second term in equation 11, and this is here. Yeah. Then here we introduce E naught cos alpha and E naught sin alpha and replace this big brackets in equation number 11. Okay. And we know that cos square alpha plus sin square alpha is equal to 1. Yeah, this holds. Yeah, if you square equation number 12 and 13 and add them up, then you will see that this satisfy they should satisfy this criteria. Yeah, from equation number 12 we can get the expression of cos alpha. What we will have to do? We will have to just divide the left and right hand side of equation number 12 by E naught, and similarly from equation number 13 we can get the expression for sin alpha, square them up and then add them up. Okay. After squaring and adding, we will get equation number 14. Okay. And if you divide these two equations, if you divide equation number 13 by equation number 12, then we will get the expression for tan alpha. Now, equation number 14 and 15, what do they give us? They give the expression of E naught and the value of alpha, which were the unknown in equation number 12 and 13. Okay. We replaced this term by E naught cos alpha, where both E naught and alpha were unknown. Similarly, we replaced this second term with E naught sin alpha, where again E naught and alpha were unknown. By using equation 14 and 15, now we can get the value of E naught as well as the value of alpha. Everything is known now. Okay. Now, if we know this, let us substitute equation number 12 and 13 back into equation number 11. Okay. If we substitute them back into equation number 11, we will get this new expression for the total disturbance. Yeah. And if you see, then this expression, if you take E naught out of the bracket and if you see this expression, then it is nothing but sin A plus B formula. Yeah. And therefore, the final expression reduces down to E is equal to E naught sin omega t plus alpha, where alpha is given by equation number 14, E naught is given by equation alpha is given by equation number 15 and E naught is given by equation number 14. All the things are known in equation number 17, and this is the resultant disturbance in the medium. Okay. If we let two waves of same frequency overlap in space and time, then the resultant disturbance will be given by equation number 17. Okay. What we see here is that the resultant disturbance, which is given by equation number 17, is again a harmonic wave. Yeah, it is a sinusoidal wave and it has the same frequency, which is equal to the frequencies of the superimposing waves. Yeah. And the amplitude is different from the earlier two superimposing waves. Yeah. There were two waves, let us repeat. Initially there were two waves E1 and E2. They were having different amplitudes, but the frequencies were the same, and the resultant wave E has the same frequency, but a different amplitude. Yeah, this is what it is written here. The composite wave is a harmonic wave and it has the same frequency as that of the constituent waves, but its amplitude and the phase are different. Yeah, the alpha is different and E naught is different. Yeah, amplitude and the phase are different while omega is the same. Yeah. Now, if you see equation number 14, then what are the informations which can be extracted out of equation number 14? E naught is the resultant amplitude, and the first term here is the square of amplitude of first wave, second term here is the square of amplitude of the second wave. But in addition to these two terms, we are having this multiplication of E naught 1 and E naught 2, and this term is called interference term. Okay. This term gives rise to fluctuation in the resultant amplitude. Okay. Some sinusoidal variation will appear in the resultant amplitude or intensity due to this term, and therefore, this term is called interference term. Okay. It means interference owes its origin in superposition principle. Okay. Now, the resultant flux density is not simply the sum of component flux densities. Flux densities means amplitude square, yeah, which we saw in equation number 14, and there is this additional contribution which we known as interference term. Yeah, this is our interference term. Okay. Now, let us talk about the phase part of this interference term, which is nothing but alpha 2 minus alpha 1. Let us represent this phase part by delta, this del. Okay. This del is equal to alpha 2 minus alpha 1. Okay. Let us assume this del is the phase, the del represents the phase of this interference term. Now, whenever del is equal to 0, plus minus 2 pi, plus minus 4 pi, the cosine function would be equal to 1, and this is the maximum value the interference term can achieve, and due to this maximum value the resultant amplitude will be maximum, and this we call a constructive interference. However, when del is equal to odd multiple of pi, that is if del is equal to plus minus pi plus minus 3 pi, then the resultant amplitude will be minimum, which correspond to destructive interference. Okay. Now, the phase difference may arise from a difference in path length traversed by the two waves as well as difference in the initial phase angle. Okay. Now, we are talking about this alpha. Now, we will substitute back the expressions for alpha 2 and alpha 1 in equation number 19, and then we will look into it. What are alpha 1 and alpha 2? Let us go back. Yeah, alpha 1 is minus, alpha is minus kx plus epsilon. Yeah, therefore, alpha 1 would be minus of kx 1 plus epsilon 1. Similarly, alpha 2 would be minus of kx 2 plus epsilon 2. Okay. Now, with this let us go to again equation number 19. Now, we will substitute this expression back in this equation number 19. After substitution, we will get this expression for the phase. Yeah, del is alpha 2 minus alpha 1, which is phase difference. Yeah, phase is a relative quantity. Okay, it is always measured with respect to some reference value. Whenever we say phase is equal to 0, it means the reference value is 0 and the phase has not evolved from there, from that 0 value. Okay. Now, you see here after substitution for the alpha 1 and alpha 2, the del, the phase difference between the two waves takes this form, which is given by expression number 20. Now, what is k? K is wave number, and the expression for the wave number k is 2 pi by lambda. We know k is equal to 2 pi by lambda. We will substitute for this expression of k in equation number 20, and this gives us equation number 21. Okay. Now, in this phase component, in this phase difference, in this expression of del, the first term arises due to difference in x1 and x2, and second term arises due to difference in epsilon 1 and epsilon 2. What is x1 minus x2? x1 minus x2 is nothing but path length difference. x1 is the path traversed by first wave, and x2 is the the path length traversed by the second wave, and x1 minus x2 is path length difference. If you multiply this path length difference by wave number, which is 2 pi by lambda, this gives us phase difference. If you multiply path length difference by a wave number, this path length difference then get converted into phase difference. Okay. Therefore, this first term represents phase difference due to the path length difference, while the second term, which is epsilon 1 minus epsilon 2, it owes its origin in initial phases of the two waves. Okay. Epsilon 1 is initial phase of the first wave, epsilon 2 is the initial phase of the second wave. Take the difference, and this difference give you the difference in the initial phases, and this is why if the wave are initially in the same phase at their respective emitters, then epsilon 1 would be equal to epsilon 2. Okay. In particular, waves for which this difference epsilon 1 minus epsilon 2 is constant throughout, such a wave is said to be coherent. We will discuss more about this phenomena of coherence in later lectures, but just to start with, a wave in which if we have two waves which have their own respective initial phases, if the initial phase difference is constant throughout the motion, the waves are said to be coherent. The waves are said to be coherent with each other. Okay. Now, for such a wave for which epsilon 1 is equal to epsilon 2, the expression for del, which is phase different, modifies, and then it becomes 2 pi by lambda x1 minus x2. Okay. Lambda is wavelength in the medium, and this lambda embeds in self the information about the refractive index of the medium, and we know refractive index n is equal to lambda naught by lambda. Therefore, we can safely write that lambda is equal to lambda naught by n. Okay. Now, we will pick this expression and substitute it back here. Okay, and this gives del as 2 pi by lambda naught into n, which is refractive index of the medium, and multiplied by x1 minus x2, the path length difference. What is lambda naught? Lambda naught is the wavelength in vacuum. What is lambda? Lambda is wavelength in a medium of refractive index n, yeah, and they are related by this relation, refractive index n is equal to lambda naught by lambda. Okay. We can easily derive this relation, n is equal to Cy from n is equal to Cyv relation. Okay. Now, this quantity n x1 minus x2 is path length difference in the medium. Okay. X1 minus x2 is the path length difference in the vacuum, but if the waves are travelling in a medium, if superposition is happening within a medium, then the optical path length difference would be n into x1 minus x2, and this is why it is called optical path difference, and this optical path difference is expressed by capital lambda. Capital lambda is equal to n x1 minus x2. Okay. And as I said, if you multiply optical path length difference by wave number, then we will get phase difference, and this is what it is written here. Yeah, this is what is written here. Here the optical path difference is related with phase difference, and this relation is through this wave number k naught. Okay. K naught is wave number in vacuum and k is wave number in media. Okay. K is related with k naught through this relation, and we know that k is equal to 2 pi by lambda, or k is equal to 2 pi by lambda naught into n, and k naught is 2 pi by lambda naught. Therefore, k is equal to k naught into n. Yeah, this is the relation which is also written here. Okay. Now you see here in the figure on left, in this figure there are three waves E1, this is E1, this is E2 and this is E3. They are of different magnitudes. Their amplitudes are different, but they oscillate with the same frequency. Now, if we assume that they are in same phase, if we assume that they are oscillating in same phase, then they will reach to their maxima simultaneously, and as well as they will reach to their minima simultaneously. They will therefore crust and trough, they both will appear simultaneously for all three waves. Okay. And therefore, what you see is that the peaks of all three waves are coinciding here, the dips are also coinciding here, the waves are simultaneously crossing this 0 point. Yeah. Here on the horizontal axis we can consider either x or t, on the vertical axis amplitude is plotted. Okay. Now, suppose one of the wave out of E1, E2 and E3 is out of phase by 180 degree. Okay, then what will happen? Suppose this red one in this right figure is out of phase, then you can see that when the green and yellow waves have their peak, the red one is having its dip. Okay. The peaks in first two waves coincide with the dip of the third one. Therefore, if you sum these three waves, the resultant will be reduced as compared to that in this first case. Okay. Therefore, what we can say is that E2 is, which is represented by red color, the wave E2 is out of phase with wave E1 as well as wave E3, while in figure 1 all three waves E1, E2 and E3 they all are in phase, they are oscillating in phase, while in the right figure E2 is oscillating out of phase while E1 and E3 are in phase. Yeah. This is all for today. Thank you for listening me.